All right, here's the quiz 6 key. First one is a transformer problem. Remember, I did say anytime you see a transformer, almost always you can, first thing is to box everything on this side, the secondary side, right? This is called the primary side. This is the secondary side. Remember that E primary or V primary is just across this transformer right here. Whereas the current I primary is what's flowing throughout this entire side. On the secondary side, E secondary is just what's on the secondary side of the transformer itself. Inside this highlighted area, that is the transformer, which is two coils that are coupled and paired. And in this class, we assume ideal. So we use this turns ratio right here, 16 to 1. A equals 16 because there's 16 times more turns on the left side than there are on the right, which means the voltage on the left side of the transformer is 16 times greater than the right side. But this reflected impedance is what it appears on the primary side of the circuit. So if I was to redraw the circuit with this, and here is that part up there, 512 plus 256J, right? Inside of this box right here is what is the reflected impedance. Z on the equation sheet, it says primary reflected. That's the reflected impedance. How do we solve for that? Z prime reflected is equal to A squared Z secondary. So the A we said was 16, so that's 16 squared. Z secondary is everything on the secondary side. So it's 2 plus 1J plus 6 plus J4 or 4J, right? And I put all those together, plug it into the calculator, and I get 2048 plus 1280J. And all that's in ohms. So from the primary side of the circuit, it just looks like an impedance. It can't tell whether it's a transformer or just some really large 2048 resistor and 1280 inductor. So now if we wanted to find the voltage across the primary side of the transformer, well, that is actually the same thing that is inside of Z primary reflected. So I see these are all in series, and I can actually just use a voltage divider rule because everything's in series. The voltage being split up is 4160 volts, angle 0. In the top, remember VDR says Vx equals VEQ times, not R, we're in AC, so ZX over ZEQ. Okay, so the ZX is what's in between the nodes. Well, that is the primary reflected, 2048 plus 1280J. And everything that is sharing that voltage, right? Everything that's sharing that voltage, which in this case is the Vx, V primary, plus that 512 plus 256. Yes, Levi, you may. 1280 plus 512 plus 256J. Put all that together, and I get 3365 angle 1.04 degrees. That's volts. So if I was being engineering notation, 3.365 kilovolts, angle 1.04 degrees. Now the question, will the load receive maximum power or not? Well, what does it take to achieve maximum power? We need Z Thevenin complex conjugate to be our Z load, right? The Z load being a Thevenin load. Well, look up here at part A. That looks like a Thevenin circuit, right? There's one impedance, that's the Thevenin impedance, and the load. Well, Z primary reflected does not equal the complex conjugate. What we would need Z load to equal 512 minus 256J. That would achieve maximum power. So this is not max power. And there's our transformer problem. Now for the second problem, we have a linear motor And remember I said if you have a linear motor, and I go to the equation sheet, everything that I need for linear motors is inside this box right here, except the only other one that we might also need would be the efficiency equation. That's the eta symbol, looks like a lowercase n, P out over Pn. So let's use these equations and solve the problem. So let's label our terms first. These are what's given. VB, that's the voltage going across or being provided into this V field. It's a magnetic field. There is B. Internal resistance, that's R of 200 milliohms. Efficiency, there's that eta that we talked about. Effective length, that is L. In the equation sheet, assume the steady state mechanical load is 1 Newton. So this is F load, but if it's at steady state, that means that we've also achieved is now equal to the force developed. That is because we are now at steady state. So the force, Lorentz force that developed is now equal to the load. And it also says right here, assume that there's no friction. I guess that's what finally makes it, because F load would be made up of the FD plus the losses of friction, but that's 0. So now those are equal to each other. So let's find the back EMF. That is the E induced. How would we find E induced? Well, I would use the equation VB minus E induced equals IR. Oh, but wait, you say we don't know I, but we can quickly get to I because we can say that the force is equal to that force developed, ILB, and we can rearrange it for I. I is equal to FD divided by LB, and that is 1 Newton divided by 0.4 meters and 0.8 Tesla, and I comes out to 3.125 amps. So now I plug that in over here. E induced is equal to VB minus IR. VB is 24 volts minus 3.125, and the R is 200 milliohms, and I get 23.375 volts. There's E induced. Next question is, what is the output power of the movable bar? The shortest equation, based off what we have, is that P out is equal to E induced times I, 23.375 amps, 23.375 volts times 3.125 amps, and I get 73.04 watts. There's my P out. But another way that you could do it, since we have efficiency, we could say P in equals VB times I, and that is 24 times 3.125, comes out to 75 watts. And then efficiency says P out over P in. So P out would be equal to P in times efficiency. 75 times 0.974 up top gives me 73.05 watts. And there's just a rounding difference. Okay, so those would both equal the same thing. Last question is, how fast does the bar move at steady state? Well, fast is velocity, which in our formula sheet is U, because V is voltage, so U is velocity. In the equation with U says that E induced equals UBL. I can rearrange that for U, and I have E induced divided by BL, 23.375 volts, divided by 0.8 Tesla, 0.4 meters, and U comes out to 73.05 meters per second. So that's this linear motor, Remember, the description is that we have these rails and we have a bar and it's moving along. And so the fastest that it achieves, that steady state velocity, is 73.05 meters per second.